All right, welcome everybody. This is the Flow seminar, where Flow stands for Federated Learning One World seminar, which was a seminar created to provide a global online forum for the dissemination of latest scientific research in all aspects of federated learning. That's included but not limited to distributed optimization, learning algorithms, privacy, cryptography, personalization, and many more. Today is my great pleasure to welcome again Grigory Malinovsky, who is currently a PhD student in applied mathematics and computational science at the King Abdullah University of Science and Technology, working with Peter Richtarik, focusing on optimization theory and its application to machine learning. And today he's going to tell us more about how Byzantine's robustness can be combined with partial participation. So thank you, Grisha, again for agreeing to give a talk. Looking forward to it. Please, floor is yours.
Thank you very much, Sam, for a nice introduction. Okay, today I'm going to present our joint work with Eduard Gorbanov, Peter Richtarik, and Samuel Horvath about Byzantine robustness and partial participation regime. Okay, sorry. Okay. So this talk is based on a recent paper. Byzantine robustness and partial participation can be achieved simultaneously. So we just clip gradient differences. And this paper was accepted to Privacy Regulation and Protection Machine Learning Workshop on ICLR 2024. Okay, this is an approximate plan of my talk. So first of all, I'm going to give a brief introduction of Byzantine robust training. After that, I will discuss robust aggregation and its properties. And after that, I will focus on the partial participation regime and our proposed method. And if you have any questions, you can interrupt me, so there is no problem. Okay, let's get started. So first of all, let me consider standard formulation of distributed training without any Byzantines. So in this setting, we have a central server and n workers connected to the server. Okay, our goal is to minimize the average of loss functions fi, where each fi represents a local loss function based on local datasets. So I believe everyone is familiar with this formulation. It appeared many times on this seminar. Okay, so the main characteristics of such formulation first of all, it's hard to solve for clients. Otherwise, there is no motivation for collaboration, and also usually clients do not communicate to each other or even do not know each other. Okay, so the simplest method for solving this problem is parallel SGD or distributed SGD. And I'm going to consider the simplest algorithm to indicate the problem of naive approach. Okay, so at each iteration k, server sends the current model xk to workers. Workers compute unbiased, but possibly biased, but it's not really important. Stochastic estimates of gradients of local loss functions and send the updates back to server. So server aggregates the updates from clients by calculating an average and perform a gradient descent step. Okay. But however, this method works only if we assume that all workers are good and honest. In practice, even if worker is honest, it can send some updates with some errors or some computational inaccuracies or our problems. Or some workers can even maliciously send arbitrary bad vectors. And if such vector knows information about our updates of our vectors, it can cancel out the whole update and move the iterate arbitrarily far from the solution. And it happens because standard averaging can be arbitrarily spoiled by even one arbitrary bad vector. And all standard distributed methods are fragile to such attacks because they use standard averaging. Okay, so let us consider refined problem formulation. Okay, we consider, so first of all, we consider two subsets. First, subset of good clients or regular clients, denoted as calligraphic G, and subset of bad workers, also called Byzantines, denoted as calligraphic B. So our goal is to minimize the average of loss functions among only good clients. And we assume that we have an upper bound of ratio of Byzantines delta is known, and it's strictly less than 1/2. Otherwise, the problem cannot be solved if Byzantines form majority. Okay, and we also assume that Byzantines are omniscient, so it means that they know all information about our loss functions and our gradients. Yes. I cannot hear you well.
Yeah, I think this was just unmuted. Somebody was unmuted. I don't think that was a question.
Okay. You can also type in the chat if you have a question. Okay. Yeah, so we assume that Byzantines are omniscient, and this assumption is quite strict. And we use it to consider the worst case scenario. And if we are able to construct a method that is robust to omniscient Byzantines, it means that this method is robust to all other settings. Okay. And we need to consider some condition on heterogeneity. Since we cannot work with arbitrary heterogeneous function, because in this case, Byzantine worker can pretend that it has very non-representative local data and it has very, very strange gradient. Actually, we have an extension where heterogeneity is bounded in more general form, but in this talk, let us consider constant bound. Okay, do you have any questions about the refined problem formulation? I'll stop here for a moment.
It seems there are no questions in the chat. Also, I don't see any raised hands, so
Okay.
please continue.
Let us move on. Okay, so how to solve such problems? The natural question. We need to use robust aggregation. Okay, and we need to replace. So we indicated the problem, and the problem is in standard averaging. So we need to come up with something more robust, and we need to replace averaging by this robust aggregator. And let us consider some examples. So first example is geometric mean. So instead of consider squared norm of differences between G and GIK, we consider only norm without power of 2. And it makes a little bit harder to calculate, but it's okay overall. Also, we can consider coordinate-wise median. So instead of considering second norm, we use first norm, and so the problem becomes coordinate separable. Also, we can use Cram estimator. So in this estimator, we need to minimize the sum of squared distances, but not among all vectors, but only to closest n minus b minus 2 vectors to G. And in this operator, we need to know the size of subset B, but we can use some upper bound on this, such as delta n, for example. So, however, in paper of Grigory and al., it was shown that coordinate-wise median, geometric median and CRAM do not converge to optimum almost surely for any number of workers, and even if none of them are Byzantine. And I will explain. So it's a theorem, so which means we have some counterexamples. And in the same paper, we showed such counterexamples. So first one is a situation when we have a quite imbalanced data set. And since middle seekers are good of filtering outliers, they consider imbalanced classes to be outliers. So it can learn only first and second class, but it cannot learn other classes. And the same situation we have with fat tail distributions. So middle seekers are bad because they consider heavy tails as outliers and ignore them. So overall, it leads to some bias, and this bias can damage convergence. Okay, we need to formulate a definition of robust aggregators that are appropriate for theoretical guarantees. So this is the definition, and it's standard definition in Byzantine robust learning. Okay, we have n random vectors, and we know that a subset of good workers is strictly larger than 1/2 of all vectors, all workers. So we assume that we're independent, and for all pairs, with all pairs I and G, we have bounded variance. And if we denote G bar as average among good clients and G hat as robust aggregator, so okay, the variance is also bounded by C multiplied by delta multiplied by sigma squared, and the intuition behind this, okay, we have some constant C, but this bound should be proportional to a ratio of Byzantines and proportional to noise. So if noise is large, it's easier for Byzantines to hide between good workers, and also if portion of Byzantines is large, it's also easier for them to make difference between aggregated and true mean be larger. Okay, and we additionally say that G hat is agnostic robust aggregator if we do not need to know the value of sigma squared to compute it. So we call it agnostic robust aggregator. And all medians and CRAM estimators do not satisfy this definition, unfortunately. But can we do something with this? Yes, we can. And we need to apply bucketing. So bucketing is a special technique to fix our robust aggregators. So we have So we have n vectors, and we need to permute them according some permutation, and after that we divide these n vectors into n over s groups, and inside such group we calculate an average, and after that we use such grouped averages for aggregator cram or medians. Okay, and it was shown that cram geometric median and coordinate-wise median with bracketing is delta C robust aggregators with calculated constants. And what is most important here, they are agnostic to sigma squared, and it's important for theoretical analysis. Okay, do you have any questions about robust aggregators? Okay, let me continue. Okay, now we go to the main part of my talk, which is partial participation and Byzantine robustness. Okay. In real world system, it is not possible to synchronize across all workers as it was shown in previous formulation. So only a small subset of workers can participate in one communication round. And in this setting, with some probability, which might be significantly high, Byzantines can form majority and destroy the learning process. So we select some subset of clients to aggregate information, and in this subset we can have a significant amount of Byzantine workers. Okay, and so how to solve such problem again? Because standard robust aggregators cannot work with situation when delta is larger than 1/2. Okay, so we need to first consider previous method, Byzantine VR Marina, which is appropriate for situation when we do not consider partial participation. And in this method, we have the following updates. So with small probability P, each client calculates the gradient nabla Fi, and with large probability 1 minus P, it calculates mini-budget estimator of gradient differences. And after that, it applies unbiased compression operator. And the server aggregates such updates, and after that, we just take a gradient step. But the problem here that an estimator GK is biased from construction, because we have agnostic robust aggregation, we have compression, we have other things together, and in the end it's biased. Okay, but as I said, robust aggregation cannot work with situation when we have majority of Byzantine workers. And so we need to use second component of our solution, which is clipping. So clipping is special operator which takes some vector x and it returns x, or x if it's if it lies outside the ball with radius lambda, or you just cut it. So it would be lambda divided by norm of x multiplied by x. Okay. And since we consider partial participation regime, we sample set of clients Sk with size of C. C is our cohort size with probability P, and with our probability, we sample small cohort size. So we have two cohort sizes. Which one is large and another one is small, and I will explain later why we do this. Okay, and here we add a special. Okay, we add here clipping. So we clip our compressed differences, and server aggregates our updates in this form. So with small probability P, we just aggregate with robust aggregation, and with probability 1 minus P, we add aggregated clipped compressed differences to previous estimator. Does anyone have any questions about clipping, how it applied here?
I have a question. Could you please remind me if those gradients are full gradients or sampled mini batches?
Okay, thank you for your question. Yeah, so delta I hat is a mini batched version of gradient differences. So let me go back. So we mini batched means each gradient nabla Fi can be represented as another finite sum of local data points, for example, or it can be some online setting, but it doesn't matter. Yeah, it's just some mini batch estimator. And here we use the same mini batch estimator.
Okay, thanks.
Okay, any other questions? Okay, let me continue then. Okay, here I need to explain the third component of our solution is special level of clipping. Standard constant level of clipping doesn't work here, and we need to come up with, in some sense, adaptive level of clipping, and I will explain what I mean by adaptive here. So the level of clipping should be proportional to the difference between updated point, current point, and previous point. And as you can see, if our method can converge, this difference should go to 0. So which means we decrease our radius of our clipping operator, and so the closer we stand to the solution, the harder clipping should be. So in this sense, it's adaptive. And alpha k+1 is some constant. And the motivation of this level of clipping is smoothness condition. So we assume that each function fi is Li smooth, which means the difference of gradients is bounded by constant multiplied by difference of points. And as you can see, it's almost the same condition as we have for clipping and level of clipping. So with appropriate constant alpha k plus 1, which should be also proportional to smoothness constant, regular clients would not be affected by such clipping, and only Byzantine workers can be affected by this. So for good, in our words, for good workers, clipping is not damaging, but it's damaging for Byzantine workers updates. So is this idea clear? And I also need to mention that we assume that all good clients or regular clients satisfy smoothness condition. Okay. And the last component of our solution is our compression. So we apply our clipping operator to the compressed mini batch difference of gradients. Because we desire to have a method which is communication efficient, and without compression it would be not that efficient. And unbiased compression doesn't. Okay, it hurts a little bit the rate, but the idea of clipping is still applicable here. And so we use unbiased compression with conic variance. So variance is upper bounded by constant multiplied by squared norm of input. Okay, let me show the whole algorithm again to see the whole picture. Okay. So okay, we have our Bernoulli distribution with parameter p. It's our trigger in some sense. In each iteration, we sample a set of clients sk, which is so the size of sk is equal to c. So if ck is equal to 0, and otherwise it's c hat, and c hat is larger than c. Okay, so we broadcast gk and ck to all workers, and okay, so each worker computes the step, and after that we compute our new estimators j ik plus 1. So with small probability it's full gradient, with large probability 1 minus p it's clipped update of compressed compressed version of mini batch estimator. And actually each client doesn't need to clip actually, because this clipping can be done on server side, but because server doesn't trust all workers prior, so we need to clip it anyway. But it's like technical moment, it's not that important. Okay, and with probability P, we just apply aggregation, and with 1 minus P, we just add our aggregated updates to the previous global estimator. So is this algorithm clear? Do you have any questions? And I can explain in details. Okay, and one important remark is when CK is equal to 1 and the full local gradients are computed by clients, we do not need to have full full participation in this case. It's enough to have a large cohort, large enough to guarantee that in this case good workers can form majority for sure. And we do not have clipping with small probability P. And otherwise we can Byzantines can form majority, and clipping can control such updates. And it cannot damage the convergence. Okay, let us move on. Okay, to prove something, we need to assume some conditions on functions. So first condition is, as I already mentioned, is individual smoothness. So okay, and we also assume that the global function f is also L smooth, and each function fi is La smooth. And okay, actually this is enough for analysis, but to have a little bit tighter result, we also assumed global hash invariance assumption. So it's similar to smoothness, but a little bit more specific to our analysis. We can avoid such assumption because it holds if assumption of L smoothness holds, but the constant L plus 1 can be better than L max or something like this. And the same situation with local hash invariance assumption. So these assumptions are not that important. They are needed just to have a little bit tighter results. Okay, and also we considered two settings: general non-convex functions and functions that satisfy PL condition to have better results. Okay, so let me show the result. For general non-convex functions, we have 1 over k convergence up to neighborhood, and this neighborhood is proportional to okay, I think it's a bad notation. Okay, because c hat is not cohort size, it's another constant. I think I need to redefine it. And it's the main idea here is it's proportional to heterogeneity level. So if level of heterogeneity is high, our neighborhood is also large. Okay, and for PL condition we have similar result, but instead of 1 over k converse, we have linear convergence to almost the same neighborhood. Okay, any questions about theoretical results?
I have a short question. I don't see delta anywhere in those formulas. Where is it?
Okay, delta is I didn't wrote the whole expression, so delta is hidden in C hat. So this neighborhood is proportional to delta.
Oh,
Yeah.
okay. I see. Thank you.
Yes, thank you for question, and I think it's better for me to write delta explicitly in this formula for better understanding. And note C hat is not cohort size, it's a large constant which is so large which is not good for presentation on slide. Okay, and important clarification here is our result is generalization of previous result of BSVR Marina without partial participation up to some constants. So if we consider full participation of our algorithm, the result would be approximately the same up to some numerical constants appeared because of technical lemmas. So we can say that up to some constant, our result is direct generalization of previous method, but it can work with partial participation regime where Byzantine workers can form majority. Okay, let me go to some numerical results. Okay, on first plot, so we demonstrate that the naive approach of using Byzantine VR Marina with in partial participation regime without clipping just doesn't work. It cannot converge at all. And if we add clipping, as you can see, it can converge quite easily. So we also in the second plot we compared full participation against partial participation, and because in partial participation we can take many more steps before we finish the epoch. So this method shows acceleration in terms of epochs, in terms of full passes over dataset. So which is good. So it depends on setting. I mean, if we count number of communications or number of communication rounds, sometimes it's different. So if we count all total communications, this is beneficial. Okay, and the last plot illustrates how clipping multiplier affects our conversions. And as you can see, if we do not have any clipping, this method cannot converge. And also we can see that there is so we can find an optimal multiplier here, because if we have quite large multiplier like 10, which illustrated by a red line, it's bad. If it's too small, 0.01, it's also slow, and for 0.1 it's the best. But so which means we can find golden middle somewhere. Okay. So let me go to final remarks. Okay, in our work we proposed a new technique that allow us to maintain Byzantine robustness and allow partial participation regime using clipping, and not any clipping, but specific clipping, which is proportional to difference between current point and previous point. Okay, and using clipping with variance reduced Byzantine Via Marina method. Okay, we can deal with majority of Byzantine workers. We also use compression to enhance even this result to make method communication efficient. And we provided our conversion results, which up to some constants are generalization of previous results. Okay, thank you for your attention. Do you have any questions?
Thank you, Grisha. If anybody has a question, please feel free to unmute yourself or post your question to the chat, and then I can read it aloud for you. Yeah, let me just start with the one clarification question about the experiments. I think you didn't discuss the type of attack that is used here.
Yeah, I think I forgot about this.
Yeah,
so type of attack is shoot back as an attack, and we used coordinate-wise mean with bucketing as aggregation methods.
Okay, yeah, maybe here I could just say that the shift back here means that essentially, like when the clients are in the majority, the Byzantines are in the majority, they'll shift their update into they are able to shift the update into the original starting point. Therefore, why you see the essentially just a straight line.
Yeah. So if we have situation when Byzantine can majority, we just stay at the point at previous point, so it doesn't move anywhere.
So one question I would also have is about future work. So can you imagine? So here, I think that something that can be considered as a main limitation is that you require that in certain rounds the good clients, they create the majority, and those are the rounds that you have a kind of a control over. So can you imagine that this could be further relaxed in the sense that you can just run methods where you know that let's say in a standard uniform sampling of the clients, where you know that in expectation the majority of the, if overall the number of Byzantine workers is less than half or less than some delta, is also going to be the case in majority of the rounds. Can you imagine that there would be a method that would also in this setup guarantee conversion, or do you think that we would need to have these rounds the same as for your method, where you actually need to have a certain rounds where you like know exactly that there is that in this round the good client will be in majority?
Okay, good question. So in this situation, the analysis becomes much more complicated. Okay, because imagine a situation when we do not have a trigger when we need to form a majority of good clients. With some probability at every round, Byzantine workers can form majority, and we need to clip updates every time, and so it means we just do not move at all. So, and as you said, okay, in expectation we can say that we have some with some probability we good clients can form majority, but it also depends on like size of cohort and like the proportion of of events when good clients and bad clients can form majority. And so for me it's not clear, because if we have if we know for sure that we have majority of good clients, so in this case we can remove clipping at all, and it's much better to have a step without clipping. And here we need to use clipping every time, because we don't know when good clients can form majority and when bad clients can form majority. So we need to use client every time, and it's not beneficial for conversions. So it's not clear if it can converge at all or not. It's not clear.
Yeah, thank you.
So maybe I do not have a clear proof or like clear lower bound or something like this. So for me, it's not even clear if it can work at all. I have some doubts about that.
Thanks. Yeah, are there any other questions, comments?
Okay, another clarification that I would like to add is, let me go back to algorithm. It's not clear if this trick with clipping can work in the situation where we do not send some sort of gradient difference, but something else. Because if we send something else, but not compressed or mini batch, but gradient difference, so it's not clear can this trick work, because for something else we might not have this condition as what is it? Sorry, as smoothness. So this trick might not work at all if we send some, let's say, momentum, or we send something else which is not smooth. Not smooth, I mean not doesn't have a Lipschitz condition. So I think in practice it should work, but in theory it's not that clear. And this is a good question for future works.
Okay, yeah. Thank you again, Grisha. And thank you all for joining today.
Okay, no problem.